Good morning, I'm Chin Chin San, number metric AN200206. The title I want to present today is the investigation of vehicle performance and exhaust emissions under low load condition. So the background study for biodiesel. Biodiesel is a processed fuel for diesel engine vehicles. It can be derived from vegetable oils or animal fats, such as palm, coconut, and castor oils. So biodiesel refers to 100% biodiesel fuel, or we call it B100. A standard diesel vehicle engine can only run on pure diesel when there are some modifications toward the engines. Pure biodiesel will condense during the cold temperature and it can corrode the seals in older diesel vehicles. So the biodiesel that we use in our diesel engine vehicles is called the biodiesel blends. So it can run the engine smoothly without audible knock, but it has lower calorific value and higher cetane number. So the advantage to use these biodiesel blends is first, portability, second, ready availability, renewable, higher combustion efficiency, and low sulfur emissions. The disadvantage is higher viscosity, higher nitrogen oxide emission, injector choking, and engine wear. First is the problem statement. So a unique frequent stop and slow moving traffic in Malaysia need a clear understanding of vehicle behavior under these circumstances. So this means the vehicle always operate in low load condition. Next is alignment with the National Automotive Policy (NAP) to introduce B30 biodiesel in Malaysia by 2025. So we need to know is that B30 is ready to use in Malaysia. So the research objective is to investigate the performance and exhaust emission by using B10 and B30 plant oil biodiesel blends under low load conditions. So the scope first is we're using the chassis dynamometer Mustang AWD 500 in Unitech. Second, we run the vehicle below 40% engine load with constant 40 km per hour speed. The fuel that we use is B10 and B30 plum oil biodiesel. The vehicle is Mazda CSX 2.2 liter with SkyActiv D technology. The significance of study. First is the performance for B10 and B30 plum oil biodiesel blends under low load condition can be studied. Exhaust emission for B10 and B30 plum oil biodiesel blends. And lastly is comparison between the performance and exhaust emission under these two type biodiesel blends. So for the literature review, for the fuel type, to determine the fuel properties, calorific value, cetane number, viscosity, density, sulfur content, and flash point. How can these fuel properties can affect the engine performance and also the exhaust emission? Next, we study about some vehicle technologies. First is CRDI engines. So IMAP will increase due to fuel injection pressure. Average reduction of 2.43% in BFFC, and final is brake thermal efficiency will increase due to higher compression ratio and injection pressure. For the turbocharged direct injection engines, low heating value of biodiesel increase the BSFC of the engine. And the total particle number concentration will decreases when we use the biodiesel blends in TDI engines. For the light duty diesel technology, higher viscosity of biodiesel will reduce the fuel injection angle and available air in the fuel injection area, which can reduce the CO2 emissions. Under the speed conditions, when the speed engine increases the brake power, brake thermal efficiency, brake torque will increase. Higher emission of HC and NO, not nitrogen oxide at lower speeds for all biodiesel blends. For the load condition, when when the vehicle in high loads, it will increase in air-fuel equivalence ratio result in an excess of oxygens, which can leading more complete combustion and improvement in engine output power. So under low engine load, the specific fuel CF SFC values for biodiesel mixture are lower than the pure diesel fuel. So the emission of carbon monoxide will show a decreasing trend from 0 to 75% loss. Lastly, we study about the SkyActiv D technologies. It has the lowest compression ratio, 14 to 1, or 20 to 30% of better fuel efficiency. So with the SkyActiv D technologies, the vehicle do not use the expensive NOx after treatment system. It has a new two-step turbocharger for smooth and linear response. Precise injection quantity and timing increase the accuracy of mixture concentration control and ensure the cool start capability. So this is some references for my literature review. So the methodology I divide into 4 sessions. First one is materials and equipment. So first one, of course, is the fuel properties for B10 and B30. We more focus on density, viscosity, Cetane number, and calorified values for the fuel. Next is the vehicle that we use is Mazda CX-8 with SkyActiv D technologies. This is the engine's specification, and this is another specification of the vehicle. So the engine displacement for CX-8 is 2.2 cc with the compression 14.4 to 1. The max power is 188 horsepower at 4,500 RPM, and the max torque is 450 Newton meter at 2,000 RPM. So these are the other apparatus that we use in this experiment. First one, the B30, we only can manually blending because we cannot directly get the B30 plum oil biodiesel from open market. So we use the biodiesel blending machine to blend between B100 and B10 Euro 5 that we get from Caltex in Pago. So next, we use the Mustang dynamometer all-wheel drive 500 model. Next, we use the Timberland's Bluetooth OBD2 with the aid of Top Pro application. Next, we use the Bosch BEA 060, which is the exhaust gas analyzer with the aid of BEA 030 speed measurement, this one, and KTS 515 OBD, this one. So the experiment setup for the pre-experiment checklist, we need to ensure all the components of the Mustang dyno are in good condition. Next, we need to check the vehicle condition such as tire health, tire pressure, so engine and transmission oil, plug, belts, and hoses is in good condition. Next, we need to identify and list the parameter in top row that need to be logged during the experiment, such as RPM, engine load, fuel flow, and the others. So next, we need to study the guideline or the manual for the chassis dynamometer software, power dyne, emission gas analyzer, and the specific vehicle under testing. Next, we need to ensure all the tools are sufficient in quantity, functionable, and properly connected to facilitate a smooth and accurate experiment. So next, we need to have a good PPE, such as wearing earplug and safety shoes during running the experiment. After that, after we check all this, we can park the CSS on the dynamometer. Then we need to ensure it is centered and straight. So implement cross stepping at suitable point to prevent some unnecessary movement when the experiment is running. So finally, we need a dyno fans, which utilize dyno fans to dissipate engine heat effectively during the test. So during the experiment, we need minimum with 3 people on the experiment, 1 to operate the vehicle, 1 to monitor the dyno computer, and lastly is record and monitor the emission gas analyzer computer. So we start with the B10 plum oil biodiesel blends first. So to run the vehicle under low load conditions, we need to maintain a constant speed of 40 km per hour that can set at the dyno application. Next, set the engine load manually to 20% using the top probe through the OBD2. So sustain each load for 10 seconds with a data collection interval of 0.5 seconds. So we gradually increase the load to 25%, 30%, 35%, and lastly 40%. Maintain each load for about 10 seconds. Record the brake power using the PowerDyne software for the dynos software. Then we collect the engine RPM and fuel flow through the top row for VMAP and VFFC calculation. So for the emission monitoring, you need to insert the emission gas analyzer probe into the exhaust pipe and record the CO2, CO, HC, and NO data at the emission gas analyzer computer application. So we need to repeat the experiment multiple times to ensure the consistency and the accuracy for the test. Minimum with 3 consistent test results. And lastly, we switch to B30 and repeat all the steps to get the vehicle performance and exhaust emission. This is some results that I take from Mustang Dyno. So as you can see, this one is at 20%, 25%, 30%, 35, and 40. So the color determine the different tests that we run. So it's very close and consistency. So we'll take the 3 data for these 3 tests. This is for engine power and engine torque. So for the data analysis, firstly, we use the Excel spreadsheet. We format collected data into an Excel spreadsheet for organized analysis. So emphasize the key parameter critical for performance and emission assessment. So we need to calculate the average value for brake torque, brake power, CO, CO2, HC, and NO under different engine loads. And we use the formula Bmap to calculate. To calculate the Bmap, we need the torque T, N is to calculate the Bmap. First, we need the torque engine displacement equal to two, 2191 cc, and N is equal to number of revolutions per power stroke, where for the four-stroke engines, N is equal to 2. To calculate the BFFC, we need fuel flow and the brake power. So lastly, for chapter 3 is uncertainty, which is the error and uncertainty may arise from diverse factors such as at selection, calibration of instrument, fluctuation, and environment condition, variations in test and observation. This is the uncertainty and error that we calculate. The top power fuel flow rate, FCCO, NO, and CO2. So this is the flowchart first. We start with data gathering and we set up for the chassis dynamometer to run the experiment. Can it proceed? If yes, we'll run the experiment with low load conditions and we take the result, and lastly we finish the reports. So this is the vehicle performance. So for the brake torque analysis, the brake torque have an increasing trend when the engine load increases. At 40% load, both B10 and B30 will exhibit the highest brake torque value. So the difference between B10 and B30 at 40% load is about 2.34 Newton meter, where the B30 is lower than B10. So the lowest brake torque value occur at 20% load for both fuel. So the observed decrease in brake torque with higher biodiesel blends, as mentioned by Rashil, it can be contribute to the lower calorified values in B10, B30 compared to B10. For the brake power increase when the load increases for both B10 and B30 biodiesel blends. So at 40% load, the peak powers recorded is 14 kilowatts for both blends, and the lowest brake power is at 20% load. So the small difference in calorified values and dynamometer sensitivity result in negligible variations between B10s and B30. So for the Bmap analysis, Bmap will increase with load for both B10 and B30 biodiesel blends. At 40% load, the peak values recorded 552.61 kilopascal, and for B30 is 539.20 kilopascal. The difference between both fuels at 40% load is about 13.41 kilopascal. So the Bmap will decrease with higher biodiesel blends due to the lower energy contents, higher viscosity, and also the lower brake torque. Because the formula we use to calculate the Bmap, we need the brake torque. So when the brake torque decreases, the Bmap will also decreases. Lastly is BFFC analysis. So lowest BFFC is at 25% load for both fuel use. So the difference between B10s and B30 at 25% lot is about 6.78 gram per kilowatt hour. And the B30 shows the lower BFFC compared to B10s. So the B30 exhibits higher fuel efficiency due to the lower fuel flow, attribute to SkyActiv-D technology with low compression ratio. So conclusion is the B30 is more fuel efficiency compared to B10 at various load conditions. So next is for the vehicle performance. This is the data. So for the CO2, the percentage volume will increase with load for both B10s and B30 biodiesel blends. So at 40% load, peak value recorded for B10 is 11.398 percentage volume and B30 is 11.550 percentage volume. The difference between B10s and B30 at 40% load is about 1.52% percentage volume. So increase in CO2 may contribute to sufficient oxygen in fuel combustion. For the CO emission analysis, the CO percentage volume show a decline trend from 20% to 25%, followed by an increase at 30% and a final decrease at 40% for both B10 and B30 biodiesel blends. So at 40% lot, lowest CO percentage volume recorded for B10 and B30. The difference between two fuels at 40% lot is about 0.002% volume. The presence of sufficient oxygen reduces the carbon monoxide emissions, aiding in a better combustion when the engine load is increases. So in conclusion, CO emission will decrease with load and higher biodiesel blends cause a decrease due to higher oxygen content. Next is for HC, hydrocarbon percentage volume, exhibit similar trends to CO, and the highest HC value is at B10 at 20% engine load with 4.317, and B30 is at 35% engine load with 1.986 ppm volume. So the maximum difference between HC value is about 2.331 part per million volume. So biodiesel with higher concentration and oxygen content will undergo more complete combustion, reducing the HC emission. So in conclusion, HC emission will slightly decrease with load and higher biodiesel blends cause a decrease with a maximum difference of 1.843 part per million volume. So lastly is for the NO emission analysis. The NO emissions will increase with load for both B10s and B30 biodiesel blends. So at 40% load, peak values recorded is 20.906 part per million volumes for B10s and 15.805 part per million volume for B30. The difference between B30 and B10 at 40% engine load is 5.101 part per million volume. The lower compression ratio in SkyActiv-D technologies will delay the combustion, which allows more even air fuel mixing and reducing NO formation. So conclusion is NO emission will increase with load but higher biodiesel blends cause a decrease due to Sky Active D technologies and oil reductions. So for the conclusions, conclusion for comparison between engine lot, the experiment was using B10 and B30 plum oil biodiesel blends to test the Mazda CX-8 2.2D performance and exhaust emission under low load conditions. So from the experiment, vehicle performance such as brake power, brake torque, and BMAP will increase when the engine load is increased for both biodiesel blends used. And the lowest BFFC value is when the 25% engine load for both biodiesel blends fuel use. The percentage volume of CO2 and part per million by volume of NO and HC show the decreasing trends for both biodiesel blends. The percentage volume of CO show the increasing trend. For the comparison between B30 and B10s, the vehicle performance for B30 will show the decreasing trends, except for the brake power, which has the similar brake power between B10s and B30, and decreasing in CO, HC, and NO emissions can be due to the sufficient oxygen in the combustion chamber with the aid of Sky Active D technologies. So Sky Active D technology with low compression ratio allow the better air and fuel mixing in the combustion process. The use of B30 did not lead to an increasing in BFFC and NO emissions as expected, but there was a reduction observed. Some recommendations for this experiment. First is determine the exact speed of the Mazda CX-8 because when the experiment, we just set manually 40 kilometer per hour speed. So we need to determine the exact speed by identifying the specific low engine load condition by conducting an in-depth analysis of real-world driving conditions. Next is conduct experiment using a chassis dynamometer with the constant force method, as opposed to relying on a constant speed approach. This is because the first challenges is the constant force is malfunction in the chassis dyno that I use in this experiment. So it's better if we can use the constant force method compared to constant speed in this experiment. Next, we can expand the range of plum oil biodiesel blends used in the test to provide a more comprehensive evaluation of the performance and exhaust emission of the Mazda CX-8 with Sky Active technologies. And finally, we can use the manually blended B30, but we need to get a certified by sending the manually blending B30 plum oil biodiesel to test to ensure it meet the exact B30 biodiesel blends fuel properties. So this is the crankchat for this MP, and that's all from me. Thank you.